All right, so in the last video we kind of talked about the three ways to think about dot products, and it kind of hinged on the fact that when you when you rotate your basis, as long as it's orthonormal, I said that this dot product, the value you get, even though the basis these components change, the dot product value will not. And so what we're doing in this video is proving that, because this is a really important part of this whole idea. So, all right, here we're going to do it. Just a quick note on notation, because I always forget how to do change of basis. I'm just going to use some linear algebra, and I always forget change of basis. So I like to write my vectors like this. So like I like to write I, J, and then like this, and then normal people, everybody just writes like, you just write a vector like this, and you'd kind of forget this part. But I like this because it's nice to say, if you multiply these two, matrix or vector wise, you get 1 times j plus, no, 1 times I plus 2 times j. So you get 1i plus 2j. And this, so now we have a scalar, and that's exactly what we want, right? If you have a vector 1i 2j, this is the same representation as this. So I just bring that up because I'm going to use this kind of notation a lot, just because it kind of helps me think a little bit. So so what we're going to do here is kind of the general case of a dot product component wise, with an orthonormal basis that is not I and j. So we're going to see what happens if we have a basis vector here and here essentially, or for example here and here, and make sure that the dot product, if you compute it component wise, gives us the same value. So here's how we're going to do it. We're going to say, let's call these L and M, and we're going to say, okay, so L hat M hat times A and B. So this is one vector, so this is going to be that scalar just like that, and then we're going to multiply it by L hat M hat times C and D. Right, so now this is just your dot product. So normally what we're hoping to get, we're hoping to get that A times C plus B times D, hoping. So A times C plus B times D will be the same as if we do a change of basis, right? If we write these vectors in terms of I hat and j hat, and then we did the dot product there, so we'd have new components. And if we do the dot product there, will it give us the same value as this? And that's what we're trying to prove. And if that's true, then what we said in the last video works. So this also kind of hinges on, let's see here. Let's say L and M. So let's do it this way. So we're going to have like a little aside. So if we write L, M, this is going to be equal to cosine of theta. Whoops, a little mistake here. Is I, j times cosine of theta, sine of theta, cosine of theta plus 90, sine of theta plus 90. Right, if you have an orthonormal basis, it has to be able, like, if you have an orthonormal basis, it has to be written, like, be able to be written like this, right? Because if you have I here and j here, no matter how you write an orthonormal basis, it's going to be the same as if you rotate these through some degree, right? And that's all this is saying, right? So I'm going to do this multiplication just so it's really clear. So we have cosine of theta I plus sine theta j, and then so that's over here, right? And then this next component is cosine of theta plus 90 I plus sine theta plus 90 j, right? And this this might take some convincing of yourself, but it makes sense because say you draw some new vector, right? Um, the x value is going to be let's see, how do we want to say this? All right, I'm going to pause there on that part. But so the key here, I lost my proof. But in any case, what we're doing here, I'm going to take this part and substitute it in for LM here and here. Right? So let's see if I can do it this way. Maybe like that. Okay. So now we have IJ cosine of theta, sine theta, cosine of theta plus 90, sine theta plus 90, right? So that is replacing this right here. So now times AB, right? So now this whole thing is going to be dotted by this again, which is replacing this now, times CD. So IJ cosine of theta, sine theta, cosine theta plus 90, sine theta plus 90, right? And so now we have a little bit of multiplication to do, but it's not bad. So, oh, and then I need my C and my D, right, from right here. C, D. So here it goes. So we're going to multiply these first and leave the IJs where they are for a second. Yeah, so IJ, J. Let's move this up. Okay. And then we have A cosine of theta plus B cosine of theta plus 90. That's A times this plus B times this is on the what is this, a 2 by 2, and this is a 2 by 1, so we get a 2 by 1. So that's on the top, and then on the bottom we have A sine theta plus B sine theta plus 90. And I know this looks a little disjointed, but it's right. It makes sense at least because when we looked up here, we had L and M times the 2 by 1 matrix. And down here, we have I and J times the 2 by 1 matrix, right? And so now we're going to multiply it by I, J. And then we're going to have, okay, C cosine of theta plus D cosine of theta plus 90. And then C sine theta plus D sine theta plus 90. So now we're at the point where we have it in terms of I and J, right? So we're at the point where if we were taking the dot product of these two, we would just take this component times this component plus this component times this component. And we are wondering if we get what we were hoping, AC plus BD. Right? And it's like, well, is this jumbled mess going to get that? And it actually will. So I'll show you how it goes. So you say A cosine of theta plus B cosine theta plus 90, right? So now it's this component times this component. So all of that times c cosine of theta plus d cosine of theta plus 90, right? And then in the dot product, you do this times this plus this times this. So I'm going to write plus, and I'm just going to write it under it, right? But it's all one thing. It's all just a scalar. So I'm just going to, maybe I'll do it over here just so it doesn't look like it's a vector that's 2 by 1. A sine theta plus b sine theta plus 90. Yep, times. I'm just going to draw a little times there. C sine theta plus b sine theta plus 90, right? So now it's like, man, I don't know if this is all going to cancel out or what it's going to do, but it does. So watch. So now we're foiling this because we have one term. That plus 90 is inside the parenthesis there. So it's a times cosine theta plus this. So now we have AC cosine squared of theta, all right? And then we have BD cosine squared theta plus 90. Theta plus 90, right? So that's this times this plus this times this. So now we need to do the cross terms. This one, this one, this one, this one. I'm just going to make sure I draw this line so it doesn't. Yep. Plus A cosine of theta D cosine of theta plus 90 plus, actually I probably should have written it like that. That's a little clearer. So now we have BC cosine of theta, BC cosine theta times cosine theta plus 90, right? So now there's a little bit, there's kind of stuff everywhere, but this is all equal to that, and so now we need to FOIL out this term. So now we need a big plus sign, and now right down here, so we have AC sine squared theta, and you're probably already seeing some things. So that's this times this, and now we need this times this, plus that one should have been a D, right? Because we had this and D. It's that D right there. It's this times that. So this and then this. So that should be a D. Let's see. AC sine theta plus BD sine squared theta plus 90 plus, now we're doing the cross terms here. So we already did this times this and this times this. So now we need to do, so AD sine theta plus 90 plus BC sine theta plus 90. And this, remember, so this is all just this dot product, and we were hoping that that's going to be equal to this. And so you probably already see this. This is AC times cosine squared of theta, and this is AC times sine squared of theta. So if you add those together, cosine squared plus sine squared, right, if you factor out the AC, so this is just AC here. Same thing happens here. You have BD cosine squared theta plus 90, and we have BD sine squared theta plus 90. So you factor out the BD. Now you have cosine squared of some angle plus sine squared of some angle. So we just have BD. And look, that's already this. So now we're kind of hoping that the rest of this stuff cancels out, and turns out it does. And I'll show you how. I gotta look up my trig identities real quick. Trig. It's this pi over 2 one. So it's pi over 2 minus, I don't think I can get it to focus. Can I get it to focus? Yeah. So sine of theta is equal to cosine, I'll just write it up here. So sine theta is equal to cosine 90 minus theta. And then cosine of theta is equal to sine 90 minus theta. Okay, so we're going to use those two. And really, we're just at the point of saying that we hope this is equal to this. And so now we have cosine theta times cosine theta plus 90. Well, that's 90 plus or minus negative theta, right? So 90 minus theta minus negative theta. So we have, well, we don't really need this, so it's plus, right? All this stuff. So AD cosine of theta times sine of negative theta, right? Plus BC cosine of theta. All my fans are live texting me. This is cool. And then cosine, where were we? We were, yep, right here, plus BC cosine theta times sine of negative theta, right? That's what this one here, and then this one here, right? And now we're going to add AD sine theta cosine of negative theta plus BC sine theta cosine negative theta. Right. Okay, so now we're at the point it's like, well, is this all even? And it is because, so we're going to factor out a BC and an AD, right? So AD cosine of theta sine negative theta plus sine theta cosine negative theta, right? So sine of negative theta is negative sine of theta, right? So now we have negative cosine of theta sine theta. And cosine of negative theta is just cosine of theta. Boom, this is 0. So now this is gone, this is gone, this is all gone. So now we're left with this. Same thing happens here. You can pull out this in front, and then this negative sign doesn't do anything, right? So they're canceled. So what we've proved is that if you change your basis, you still, all you have to do is write AC plus BD. And yeah, I think that proves that this A, B, and C, D are written in a different with different basis vectors. But even with that different basis vector, all you really have to do is do those component wise. So that's all.